Welcome to Aksharashala. In this video, I am going to introduce read-only memory and random access memory and their organization. Read-only memory is a semiconductor memory device used to store information which is permanent in nature. It has become an important part of many digital systems because of its low cost, high speed, system design flexibility, and data non-volatility. The read-only memory has a variety of applications in digital systems, such as it is used to implement combinational logic as well as sequential logic. It is used to implement character generation. It is used to implement lookup tables in FPGA. It is used to implement microprocessor program storage, etc. ROMs are well suited for large-scale integration manufacturing processes and are available in many forms. Two major semiconductor technologies that are used for the manufacturing of ROM integrated circuits are: first one is bipolar technology, second one is MOS technology. In general, bipolar devices are faster and have higher drive capability. For bipolar devices, output current is very high, so these are used to drive more number of devices, so they have higher drive capability. Whereas MOS devices require less silicon area and consume less power. With improvements in MOS technology, it is now possible to make MOS memories with speeds almost comparable to those of bipolar memory. The process of entering information into a ROM is referred to as programming the ROM. Depending on the programming process employed, the ROMs are categorized as: first one, mask programmable read-only memories, which are referred to as ROMs. In these memories, the data pattern must be programmed as a part of the fabrication process. Once programmed, the data pattern can never be changed. These are highly suited for very high volume usage due to their low cost. Programmable read-only memories, which are referred to as PROMs. A PROM or PROM is electrically programmable. That is, the data pattern is defined after final packaging rather than when the device is fabricated. The programming is done with an equipment referred to as PROM programmer. Second one is erasable programmable read-only memories, which are referred to as EPROMs. As the name suggests, in these memories, data can be written any number of times. That is, they are reprogrammable. Reprogrammable ROMs are possible only in MOS technology. For erasing the contents of the memory, one of the following two methods are employed. First one is exposing the chip to ultraviolet radiation for about half an hour. Erasing electrically by applying voltage of proper polarity and amplitude. This is the second method. Electrically erasable PROM is also referred to as E2PROM or EA-ROM, electrically alterable read-only memory. Now let us see organization of ROM. A read-only memory is an array of selectively open and closed unidirectional contacts. Selectively open. I want to open this unidirectional diode. I want to close this. So this is an array of selectively open and closed unidirectional contacts. So the address decoder of this figure is usually divided into two parts. This is lower decoder, this is upper decoder. Here two inputs are there for lower decoder. So by using these two inputs, four possible combinations you will get for 0 0, 0 1, 1 0, 1 1. So 0 0 is used to activate this 0 row. This is 0 1 is first row, 1 0 second row to activate second row, and 1 1 to activate third row. This is upper decoder. Here also two inputs are there. So by using two inputs, we can activate one of 4 columns. So here address decoder is usually divided into two parts for simplifying the decoder design. One half of the address lines, here one half of the address lines are decoded by one decoder used to energize one of the 4 rows, whereas the other half of the address lines, these are the other half of the address lines, are decoded by this another decoder. These are used to activate columns, these 4 columns. This method of addressing is referred to as two-dimensional or XY or coincident selection or addressing. A unidirectional switch is incorporated at the junction of every row and column. You can see at the junction of every row and column. So this is row and this is the column. At this, one switch is unidirectional switch is incorporated at the junction of every row and column. To select any one of the 16 bits. So totally here how many bits are there? 16 bits. This is these are 4 bits. Here in column wise 4 into 4, total 16 bits are there. To select any one of bit, 4 bit address lines are required. For to select 16 bits, 4 selection lines are required. So a 4 bit address A3, A2, A1, A0 is required. The lower order bits A1, A0, this is lower order bits are decoded by the decoder DL, which selects one of these 4 rows, whereas higher order 2 bits A3, A2 are decoded by decoder DH, which activates the one of 4 columns, sense amplifiers. The diode matrix, here you can see this is called diode matrix. This is called diode matrix is formed by connecting one diode along with a switch between each row and column. For example, the diode D21 is connected between row 2 and this is column 1. D21 is connected between row 2 and column 1. Here first suffix represents row, second suffix represents column. So the output is, here data output is enabled by applying a chip select, by applying logic 1 at chip select input. Then data output will be enabled. Programming a ROM means to selectively open and close the switches in a series with the diodes. For example, if the switch of the diode D21 is in closed position, and if the address input is 0110, this first 2 bits are upper bits A3, A2. The lower bits are A2, A1, A0, and these A1, A0 are 10 means 2. The last 2 bits represents row. So 10 means second row. So it is connected between second row. 01. So it is 01 means column 1. So this particular line. So if the address input is 0110, row 2 is activated, connecting it to column 1. So row 2 is activated and it is connected to column 1. Also the sense amplifier of column 1, is enabled, which gives logic 1 to logic 1 to data output if chip select is 1. This shows that a logic 1 is stored at the address 0110. On the other hand, if the switch off diode D21 is opened, logic 0 is stored at the same address 0110. If it is closed, logic 1 is stored in the given address. Otherwise, logic 0 is stored at that address. Let us do one problem. In the 16-bit ROM of previous figure, the switches of diodes D00, D03, D12, D13, D21 and D33 are programmed as closed. These diodes are closed. Find the bit stored in each location. So 16-bit means totally 4-bit address lines are required. So by using 4 bits A3, A2, A1, A0, so all possible combinations first you can write 00, 002, 1111 you can write. So all possible combination for 4-bit first you have to write. Here in here first suffix, second suffix. Here first suffix represents row and second suffix represents column, right? So your first suffix means A1, A0. First suffix A1, A0 and second suffix is A3, A2. So D00. So both are 00s. For this combination, logic 1 is stored. For A1, A0 is 0. A3, A2 is 1, 1. 3 means 1, 1. So 1, 1, 0, 0. 1, 1, 0, 0. So 1, 1, 0, 0 combination. For this combination, logic 1 is stored. Again, D12. D12 means here 2 means 1, 0. 1, 0, 0, 1. Here this is 1, 0. Here 1 is 0, 1. So 1, 0, 0, 1. So 1, 0, 0, 1 combination. For this combination 1 is stored. Again D13, similarly D13, D21, D33. For these bits only logic 1 is stored. For other bits, so D33 means 1, 1, 1, 1. So 1, 1, 1, 1. For this bit stored is logic 1. For remaining diodes, logic 0 is stored. In this way, we can find the bit stored in each location for a given problem. Read and write memory. Many digital systems require memories in which it should be possible to write into or read from any memory location with the same speed. In such memories, the data stored at any location can be changed during the operation of the system. This type of memory is known as a read or write memory and is usually referred to as a random access. The read-write memories or random access memories are fabricated using bipolar devices as well as MOS devices. There are two types of RAMs. These are static RAM, also called as SRAM, and dynamic RAM, DRAM. Bipolar RAMs are static, whereas MOS RAMs can be static or dynamic. The basic storage cell of a static RAM is a bistable circuit. Bistable circuit means it is a latch which simply consists of two cross-coupled inverters as shown in this figure. So output of first inverter is connected as input to second inverter, and output of second inverter again connected to the input of first inverter. So this serves as a basic bistable circuit or latch. This is the basic storage cell of a static RAM. A RAM is an array of these storage cells requiring as many flip-flops as the bit storage capacity of the RAM, which is usually a large number. The storage cell of a DRAM is simply a capacitor. But the problem with capacitor, so the capacitors leak charge. That is the problem with capacitor. Therefore, only MOS devices can be used for dynamic random access memories. Since capacitors leak charge, therefore the voltage stored in it gets reduced with time, which requires periodic refreshing. In general, bipolar RAMs are faster than the MOS RAMs. With improvements in the MOS technology, it has become possible to make MOS RAMs with speeds almost comparable to those of bipolar. Let us see bipolar RAM cell. This is the basic bipolar RAM storage cell. In this flip-flop, one transistor is on and then the other transistor is off. When the off transistor, suppose if on transistor is forced into on state by applying a external triggering pulse at the base of the off transistor, if you apply a positive spike at the base of off transistor, which makes the off transistor into on state. Whenever it is turns on, so automatically second transistor, which is initially on, will become off. Thus, it has two stable states which are used to store information in the form of logic 0 and 1. Special features are incorporated in this cell for addressing the cell, writing into it and reading from it. So if you draw this inverter separately, it looks like this circuit. Suppose if A equivalent to 0, then PMOS transistor will become on, NMOS transistor will become off. Then this output is connected to VDD like this. If A equivalent to 1, PMOS transistor will become off, NMOS transistor will become on, then output is connected to ground. This is the CMOS inverter and its operation. Now let us see read operation, how read operation is carried out in SRAM. Assume that the content of the memory is Q equivalent to 1. So the read cycle is started by pre-charging both the bit lines BL and BL bar to logic 1. So generally the read cycle is started by pre-charging both the bit lines BL and BL bar to logic 1. Then asserting the word line WL equivalent to 1, which enables both the transistors T5 and T6. These are the access transistors. The values stored in Q and Q bar are now transferred to the bit lines BL and BL bar. At its so BL transfer to the bit lines by leaving the BL bar at its pre-charged value and discharging the BL bar through the transistor T5 and T1 to ground. So BL bar is connected to logic 0. On the BL side, so through it is connected to VCC through transistor T6 and T4. So BL bar will be at logic 1. BL will be at logic 1. Suppose if the content of the memory Q equivalent to 0, the opposite will happen and BL bar would be pulled towards VCC and BL towards 0. In this way, read operation is carried out in a 6 transistor CMOS SRAM cell. Now let us see how write operation will be carried out in CMOS SRAM. For writing into the cell, the bit to be stored is applied at BL and BL bar. When the word line WL is asserted, the value to be stored is latched. The new bit replaces the earlier bit stored. Now let us see MOSFET dynamic RAM. DRAM cell. The earlier DRAMs were made using 3 transistor cell, which were later replaced by 1 transistor cell. This figure shows the 1 transistor DRAM. In the cell, data bit stored in a small capacitor rather than in a latch used for SRAM cell. Also in this cell, only 1 transistor and a capacitor are required per bit. So whereas in SRAM, it requires 6 transistors per bit. So this allows DRAM to have very high density in comparison to SRAM. The main disadvantage of DRAM cell is that since the charge is stored in a capacitor, the capacitor cannot hold it over an extended period of time. Therefore, the stored bit cannot remain unless the charge is refreshed periodically. This requires additional circuitry. So this figure shows DRAM cell along with simplified circuitry for read, write and refresh operations. So now let us see how read operation is carried out in DRAM. For reading and writing operation, the word line is to be selected, which switches on the transistor. The output enable bar OE bar is always kept low. OE bar is low means OE is always logic 1, which enables the output buffer. So which output buffer is again connected to bit line. Bit line is connected to charge across the capacitor. So bit line is same as the voltage level on the capacitor. So again, if voltage across the capacitor is connected to bit line is connected to output data output buffer. Thus the output is at logic 1 corresponding to the capacitor charged, and logic 0 corresponding to discharged capacitor. Let us see write operation. With the row line selected, first you have to select row line, and the write enable bar is low. That means W is always 1, which enables the data input buffer. If the D in equivalent to 1, the capacitor gets charged to logic 1 through this on transistor, and the capacitor gets discharged through the on transistor to logic 0 when D in is 0. When W bar is made high, the charge on the capacitor remains trapped on the capacitor, either 1 or 0. For any queries, please contact aksharshala@gmail.com. For further updates, please subscribe to Aksharshala. Thank you.